All right, we're going to do a galvanometer this time. So, a the microphone was a generator. Uh, the galvanometer is basically a simple motor. So let's see how that works. Uh, the idea is we have a voltage going through some circuit, and so there's current going through there, and you want to know how much current's going through. All right, so the current goes through these coils, and then this thing will basically picture there'll be some needle and probably a calibrated screen of some form, but it'll go or calibrated dial, and in proportion to the current, the needle will go the, and dial in the amount of currents that's there, and it comes off and does this. Okay, now uh, as I said, this is sort of like a motor, but not quite. So let me just go to this picture. You'll see here there's a spring. So here's what they're trying to show. Uh, you have current comes in here, and it's going to make it, we'll go through the geometry here shortly, but it's going to make it want to rotate like this. So here's this. So you have in bearings, you've got these this coil, just like you see here. Okay. And so here's north, here's south. So the current's going across. Uh, current's coming in, coming out. So that's why I have I here. Okay. So L, where positive L is along the direction of the current. So if you look at, picture something coming out, you take L with your right hand coming out and rotate. Okay. And so what you get is a force this way. If you looked at coils just right here, one coming out. So you have the coil coming out, flux going that way, that produces a force going this way, which gives us a clockwise torque for what we have here. So picture that here. So this rises, this side falls. Now, so when you're looking at how much conductor is in here, so this is one turn, okay, and then you could have, this one goes to this one, comes out here, goes there, as it wraps around. Okay, all of this part of the winding is outside of the magnetic field. So picture that somewhere outside the field it comes out and wraps around and then goes into one of those. So this part and that part have no effect. Okay, now all of this will have mass, so we have inertia to this whole thing. All right, but we don't want a motor, we're trying to measure current. So this shaft will then be connected to a spring so that as the torque's created, the spring won't let it spin freely, so it'll be working against the spring, and so as it goes in proportion to the current, there'll be a torque created until it's offset by this rotational spring, and then that'll all be calibrated to some sort of dial to show you how much current there is. So that's what's going on. So the amount of conductor is for every turn, there will be 1L, 2L. Okay, so notice that. I have a note here. Each loop, one rectangular turn, yields two conductors. So if I have N coils, there's two N conductors because there's one on each side. Okay, so that's the conductor side. And so we can picture what's going to happen. EI, the unit of voltage, it goes through some, uh, and the device has, and this device itself will have its own characteristic. We'll just let this R be part of this thing's characteristic resistance. It'll have its own characteristic inductance, and then there'll be the voltage drop caused by movement. That's what the back voltage is related to. Velocity here with back voltage is VLB. We'll talk more about that in a minute, and it comes back. So this thing would have its, we'll look at the current that the system's own inherent properties would cause this thing to rotate. So it has its own R. We'll let there be a L. Let's see, I have an L put in here from when I've taught the course before. I'm like, yeah, you should have some inductance as part of this model. And then we have the back voltage. Let's talk about the back voltage. So we've noted that there would be a force on this side of this thing going up, that means there will be a torque, so the movement will be like this. So if I'm sitting over here, I need to use my right hand, but this is very awkward, velocity going up, and this would be V cross B, so I've got B going across here, so up, rotate the right hand, the thumb points in. So that's saying that increased voltage is going in against the current flow. Well, that's exactly what's happening. So we go from low to high voltage this way, the current goes through. At the high voltage, it comes down. So the increasing voltage is against the flow of the current. And that's because this is, like a motor form. Generator, they go in the same direction. Okay, so this all works. We've discussed that, so it's time to do the model. All right. We know we've got this torque this way, so that makes sense. Okay, that's F equals L cross B. Everything's at right angles, so we don't have to worry about signs. So here we go. Force I, B, and then 2L times every one of the turns. That's what we just talked about. 2N. For every time you wrap around, you get 2 conductors, so 2NL. Okay, if I multiply that by R, this radius from here out to here, I get the torque. Okay, now the back voltage, VLB. Okay, the velocity will be whatever, here we have theta, so theta dot, R theta dot will be the velocity here. L, 2NL, B. So here's the back voltage, there's the force. Okay, which creates the torque, so this thing spins. All right, so now let's work out our model. Okay, we have J theta dot, double dot. Okay, we have the torque, input torque, this is right here, 2I, B, N, L, R. Okay, and then we have we will have, it's not marked here, but notice how we have a B theta dot. That will just be the damping that's apparent within the bearings. Okay, B minus B theta dot. So I'm not going to put a B in there because they look the same. It's too hard to discern. But you have damping in the bearings minus K theta. So this side of the spring is fixed to the wall. So you have, as this thing goes in a positive direction, this opposes it. So minus K theta. All right, so we have Js squared plus Bs plus K theta of S. And then here is, as a function of current, is the torque. All right. Now, we have this circuit. So a voltage is applied. So we have R, L, and then we go through this EB. Okay. We've done that already. R theta dot 2 and LB. There's that. And then we have going in impedance, R times I, and LSI. Okay, so this is this in time. I take it to the world of impedance. So here's the I of S. I'll factor out the I, and then I can go over here, and look, I have I relative to theta. So I can bring this over, and so I can substitute in for what this is, the I. Then I have RS, because that's theta dot, 2 and LB. There's that whole piece. So I can now, here's theta, here's input. I can factor out the theta, bring the EI over here, and take everything else over to the other side. And there's the transfer function. For angular position as a function of input voltage. Next up, motors.